Now, very important aspect in understanding these processes is called indicator diagram. This diagram is basically PV diagram, that is pressure and volume graph. That relation and the graphical representation actually explains us what type of process a given system is undergoing and what exactly is the change. For example, first I'll write the topic what we are doing. This is PV indicator diagram. Okay, so how does PV indicator diagram work? Consider a gas or the enclosed system of gas where I am representing pressure here and volume here. Okay, consider the gas to be at initial pressure and volume to be P1 V1. Suppose this point represents P1 V1. This is the initial state of gas. Now suppose the pressure decreases or volume increases. Let's say both is happening. Pressure is decreasing and volume is increasing. So pressure as denoted on y-axis is going to decrease. So this point is going to subdue somewhere down, and the volume is increasing. Volume represented on x-axis is increasing. That means the point which was here now goes to here. So pressure and volume, pressure decreasing, volume increasing, the point will be something like this. So PV diagram is, the graph would be something like that. Okay, so this PV indicator diagram is very helpful in determining the change of state of any type of system, and it also explains us the type of change or the type of process through which the system is undergoing the change. That means whether the change is through adiabatic process, isothermal process or other process. Okay, let me tell you how do we take these two processes under consideration. I am writing isothermal process, and one side I am writing adiabatic process. Okay, so as I have already stated, I will repeat it again. Isothermal process is that process in which pressure and volume of a gas changes at constant temperature. That means both P and V are changing, but T remains constant. Okay, now as according to the universal gas constant formula, that's the ideal gas equation, PV is equal to nRT. We are going to take note from this equation again and again. Okay, this is an ideal gas equation. Now in isothermal process, there is no change in temperature. That means this is constant. Again, R was already a constant and number of moles of a gas is also constant. That means the equation of isothermal process would be given with this equation, PV is equal to constant. This is the main equation of isothermal process. Now there are two essential conditions for isothermal process to take place. Number one is that the walls of the system should be perfectly conducting so that the transfer of heat from system to surrounding can take place very easily. Walls should be perfectly conducting, right? Or conducting, or what are conducting walls known as diathermal walls, right? Secondly, the process should take place at very slow speed or very slow pace so that the time taken to compress or expand the gas do not affect the change in temperature of the gas. Suppose consider a piston or cylinder with a piston in which a gas is there, right? I am compressing the piston, so what will happen? I will be compressing the volume, like volume is getting low. So during compression, pressure will increase and pressure will ultimately increase the temperature. But the same thing is done at a very slow pace. The temperature will still remain constant because whatever temperature has increased in the system will get transferred to the surrounding because of the presence of such kind of walls, right? So this process should take place at very slow speed, right? Now in adiabatic process, the equation is given by, adiabatic process is what? It is the process in which pressure, volume along with the temperature change of a system takes place, but the heat do not enter or leave the system. That means P, V and T all are changing, but there is no heat intake or outgoing of the system. So equation of adiabatic process is given by PV raised to power gamma is a constant. Now what is gamma? Gamma is the ratio of specific heat capacity at constant pressure Cp upon Cv upon the specific heat capacity at constant volume. It is denoted by gamma Cp upon Cv. Again, what is gamma? ratio of specific heat capacity of a gas at constant pressure to the specific heat capacity of gas at constant volume. So PV raised to power gamma is a constant. This is the equation which represents the adiabatic process. And what would be the two conditions necessary for adiabatic process to take place? First would be opposite to that walls should be perfectly adiabatic or non-conducting. All right, walls should be perfectly non-conducting, and secondly, the speed should be very fast. The process should be done so fast so that there is no time for heat to escape through the system, right? Suppose the same piston and cylinder case as I explained in this step. This is a cylinder in which we have a piston here, and this is these are like gas particles, okay? Now, if I press this piston with a very slow speed, consider this case that these walls are perfectly conducting. So due to increase in pressure, temperature will increase directly proportional. But if given sufficient time for system to take place, that temperature is going to get released from the surrounding, right? Get released from these walls and will be equal to the temperature of surrounding. So temperature will keep increasing, but it will at the same time will keep getting transferred to the surroundings. So the temperature of this system will remain constant. But if the same process is done with a very fast speed, like I suddenly push this with a very high force, what will happen? Everything will change. Pressure, volume, temperature will change. Also, since these walls are adiabatic in this case, there will be no heat exchange. That is, heat will not escape from system to surrounding. Also, the benefit of doing fast is that heat needs some time to get transferred from system to surrounding. So even that would be eliminated. So these are two important processes, and these are the equations through which these processes are represented.